everyone. Thank you so much for joining our webinar today. My name is Anya, and I'm part of business development team at K-Mine. As we begin, I'd love you to stay connected by following our LinkedIn page, where we share our latest updates and information about future webinars. Thank you for joining us. So today's webinar focuses on seam 3D modeling, and we'll explore how seam deposits with their multiple layers and often demand considerable time and effort to develop an accurate geological model, one that reliably estimates reserves and supports efficient mine planning. The geological data that fuel 3D seam modeling come from a wide array of sources. This includes topographic surveys, drilling outcomes, geological cross-sections, interpreted geophysical and geochemical survey data, outcrop maps, contour charts of bed floors and thicknesses, geological maps, and assortment of specialized geological diagrams, and plus experimental data and just observations gathered from quarries and mines. This information arrives in different formats, ranging from raw databases and graphical illustrations to text-based reports, images, and detailed models. But first, let me introduce you to K-Mine. The company was founded in 1994, and since then we've grown quite a lot across Europe, United States, and Canada over the years. And our team brings together a diverse group of specialists, developers, geologists, and mining engineers. And we serve a broad spectrum of clients, from small exploration teams to large corporations, delivering top quality and cost-efficient solutions tailored to their needs. But at K-Mine, we specialize specifically on software designed for the mining industries, and it supports every stage from exploration through production. And we're offering 12 models that work seamlessly for open pit and underground mining. And what makes our solution unique is its adaptability. Whether you're running a small operation or overseeing a large corporation, you can choose the models that best suit your needs, starting just from one or all 12. These models cover essential tasks like managing geological data, conducting surveys, creating optimized mining plans for both short-term and long-term projects, plus with integration options for IoT devices and dispatch systems. Our software enables real-time monitoring to keep you in control. But the software was actually created from real-world industry experience and from challenges that we encountered through our consultancy work. As I mentioned earlier, we have a very diverse team, and many of them are qualified persons who deliver reports compliant with NF 43101, SK 1300, and JORC standards tailored to project stages like pre-feasibility study, mineral resource estimation, preliminary economic assessment, and others. We bring extensive expertise across a wide range of hard rock commodities with a particular focus on critical minerals. If you'd like to explore how our services can benefit your project, feel free to drop a comment below or reach out via our contact form on our website. All right, so let's walk through what we covered today. First, we're going to dive into gridded seam modeling and compare it with a HARP model. Then we'll talk about how seismic surveying and geophysical logging come into play. From there, we'll move into the difference between structured and unstructured deposits. And after that, we'll get into the other stuff, like faults, seam splitting, washouts, and all those tricky features that can throw off seam continuity. And to wrap up, we'll touch on geostatistical methods and simulation techniques. So first, I want to say that throughout this presentation, I will use the terms seam and stratigraphic interchangeably, and same goes to the terms drill holes and boreholes. So don't get thrown out of if I will use these different terms that maybe you got used to say more drill holes than boreholes, but I will use them interchangeably. So very few software packages actually offer a fully integrated stratigraphic modeling. Even fewer can extend that capability into project production planning, and K-Mine stands out as one of those rare solutions. So let's explore the GIS tools available today and dive into what sets various 3D modeling, seam modeling algorithms apart. Certain software solutions have tackled the challenge of bed correlation in 3D seam modeling by employing gridded seam modeling, or GSM. Grid-based modeling approaches work by first calculating new interpolation points as a weighted average of the original geological data, and then forming grid spaces to define geological domains. These methods rely on a series of two-dimensional matrices where each grid represents either surfaces or specific values. The blocks of these grids remain consistent sizes in the x and y directions, often rectangular, but in the z direction there is just one block per bed with its height determined by the bed thickness. As a result, bed surfaces emerge from interpolating a collection of unevenly spaced data points into a uniform fixed matrix known as a grid. The specific interpolation technique used within the grid can vary depending on the software in question. These methods are tailored for seam deposits like coal seams, thin phosphate layers, or limestone beds where the horizontal spread far exceeds the vertical thickness, posing computational hurdles for traditional 3D block modeling approaches. The next effort in addressing stratigraphic modeling challenges involves automatically generating a block model using the defined surfaces of a layer's roof and floor. Certain software solutions tried building a cubic block model with the uniform cube sizes along the z-axis starting from the grid model. However, this approach resulted in layer boundaries taking on jagged, stepped appearance. To smooth out these contacts, the block sizes in the x and y directions were shrunk, which increased the total number of blocks and made it less practical for systems with limited computing power. An alternative approach is the adaptive regular prism model. The Horizon Adaptive Rectangular Prism 3D model is a hybrid stratigraphic block model designed to more accurately represent the shape of interpreted boundaries compared to the traditional cubic block model. K-Mine has developed algorithms following this methodology. In K-Mine, the screen displays a stratigraphic block model in the form of an adaptive prism along with its attributes. Each HARP model block consists of 10 points, 5 on upper surface, 5 on the lower. Structurally, the block is a combination of a prism with two pyramidal bases, and it features 4 edges along with the central fifth axis. And the central axis helps smooth boundary transition, eliminating the step effect seen in conventional models. As a result, it enables a height interpolation and provides more precise representation of layer thickness. Each individual HARP model block contains information such as the bed or stratigraphic horizon name, location, thickness, volume, potentially thousands of additional attributes similar to cubic model blocks. By integrating the strength of grid modeling and triangulation modeling, block modeling, and grade estimation, the HARP model unlocks numerous new opportunities for geologists. One key advantage is the ability to rapidly update the model as new data becomes available. Notable improvements in modeling methodology with the HARP model includes enhanced representation of complex normal, reverse and thrust faults, the ability to store additional analytical, geotechnical, and design variables within each individual block, advanced visualization capabilities, and precise volume and resource calculations for complex 3D pit or mine models. These investments improve efficiency in both long-term resource modeling and short-term weekly geological modeling, seamlessly supporting mine planning. Creating a model in K-Mine requires only the sequence of layers and creation of a reference surface for one layer as a marker. So using this base surface, the software calculates the thickness of all other layers, both above and below. A distinctive feature of this block model is that blocks vary in size along the z-axis. The height of each block is determined by interpolating the thickness of a given layer from neighboring drill holes. This ensures the model accuracy replicates the shape of geological layers in three-dimensional space And for deposits with a simple structure, model creation takes only a few seconds. To enhance model accuracy, users can incorporate additional reference objects alongside with the marker layer. This may include maps of layer outcrops of the surface, topography surfaces, oxidation zones, and fault zones. In this approach, implicit modeling is used to generate the base surface of the quaternary sediments, which then serves as a foundation for constructing a seam block model. This helps refine layer interpolation, and particularly in the near surface zone. When dealing with the flat line information without faults, model creation is more straightforward. However, real-world geological structures are more complex. For instance, consider a deposit with two fault systems. These faults divide the field into three distinct tectonic blocks, where position of the marker layer and the thickness of the layer can vary significantly within each block. If the model is built across the entire field without restricting it to the boundaries of the tectonic blocks, the result may be an inaccurate representation, artificially depicting faulting or plicative tectonics. In the presence of faults, upthrust, and displacement, a marker surface must be created separately for each tectonic block. The solids of these blocks are then used as constraints before interpolating the layers across the entire model. This approach allows the model to accurately reflect significant displacements, amplitudes in the layer position, and thickness at fault boundaries. Layer thickness is calculated using the inverse distance weighting method, and users can refine the interpolation by adjusting the number of drill holes considered or modifying the weighting exponent. Additional modeling settings include anisotropy parameters for directional searching, contact validation tools to refine layer boundaries based on known values in exposed areas, and auto customization options to enhance model accuracy. With additional samplings applied to the selected type of workings, the actual positions of the top and bottom of seam intersections are taken into account. For example, on the left figure, with the bottom of guide C3B or blue line is shown when the drill hole add is used as additional sampling. In this case, the algorithm directly considers the actual intersection of drill hole add with the bottom of guide seam 3B in 3D space, without interpolating the seam thickness based on adjacent drill holes. In the contrast, the right figure illustrates the bottom of guide seam 3B or blue line in the guide seam elevation mode without using the additional sampling field. Here, the thickness of guide seam 3B in the add drill hole is interpolated using the inverse distance method, relying on three adjacent drill holes. As a result, the calculated bottom of seam 3B is positioned 2.5 meters lower in the section. So when working with the wedging out layers, there is an option to refine the process using an auxiliary checkbox. The pinch out seams checkbox controls how rock pinch outs are handled based on the drill hole intervals. If it's unchecked, pinch outs are generated where there is no rock interval in a drill hole. If it's checked, the pinch outs are placed horizontally halfway through the drill holes where the pinch out occurs, and vertically at the center of the pinch out rock's thickness. A unique challenge for the interpolation algorithms of layer models arises when dealing with areas that have steeply dipping layers and overturned stratigraphy. To handle these cases, we've introduced additional features like additional marker and inverted sequence. You can add another wireframe surface in the additional marker column to correctly calculate the thickness of steeply dipping seams when building a seam block model. The wireframe surface should be parallel to the bedding surface, and the auxiliary surface helps account for the dip angle in the block, ensuring the seam thickness is interpolated perpendicular to the surface. The example below shows the position of the auxiliary surface in the vertical section, which is in blue. Additionally, you can use the inverted sequence checkbox when the seam sequence is reversed within a tectonic block, such as in the flanks of overfolds or line faults. And for example, block A has a direct sequence of seams from 1 to 5, while the sequence in block B is inverted. In this case, when creating the seam block model, you can check the box in the inverted sequence column in the Blocks tab under the settings for block B. Accounting for the true thickness of formation when creating formation block model remains a challenge for many software products. And when vertical drill holes are present, the vertical thickness along the drill holes is considered in the thickness interpolation. However, this can be problematic for steeply deep formations, as the error in thickness calculation can be quite significant in such cases. Some companies propose modeling by vertical thickness first and then adding the true thickness attribute to the block model and interpolating this value through the drill holes. To do this, the true thickness must be recalculated for each interval in the database using formulas that incorporate azimuth values and the angle of incidence or angle at which the core central line meets the bedding surface. K-Mine has developed a solution that calculates the true thickness directly within the block model. So here how it works. Normals are created from the faces of the 4 upper and 4 lower triangles at the base of each block's prism. Then the average is calculated, the upper and lower planes are constructed, and from the center of mass, 2 perpendiculars are drawn, and the arithmetic mean of these 2 perpendiculars are used as the true thickness, which is then assigned to each block in the model. Last year, we introduced a new feature to the algorithm. It's called correction markers. And this settings allows you to fine-tune the thickness and position of the bed floor in the most challenging areas of the field. To use this, first create a wireframe surface from the bed floor in the areas where you want to adjust the contact positions and, as a result, the bed thickness. The algorithm will incorporate the triangulation points from your surface to when building the block model. We've also developed some useful solutions for cases when you need to transform a block model into the set of wireframe surfaces and obtain a set of local areas where no drill holes are present. To perform the transformation, simply select the appropriate mode and create either a roof or the floor for the layers. And the system will automatically generate a set of all available variations based on the specified attribute of the block model. On the flip side, if we have a set of wireframe surfaces or solids that define the boundaries of the layer, we can create a virtual drill holes along the surfaces and automatically load them into the database. To do this, simply specify the profiles with lines. A virtual vertical drill hole will be created at each point along the line, and the color table will use the X and Y coordinate of each point, and the Z coordinate of the wells will be associated with the first surface it encounters. The resulting virtual drill holes can be generated as a report table or exported to an XLS file. You can also save the results to the database, allowing you to later use these drill holes to create a model alongside the exploration boreholes. First, in the reference table of the database, specify the names of the varieties, like layers or domains, and these names should match the names of the sublayers in the layer editor where the corresponding solids or surfaces are saved. All rock varieties will automatically be added into the assay or the lithology table with thickness calculated and interval defined from and to. Then we can visualize the drill holes. The names will have the prefix of the layer name from the layer editor, followed by an ordinal number for each point as a suffix. So let's view the results in the section. We'll see the boreholes labeled base 1, base 2, and so on. And a common question that comes up is about splitting coal seams during modeling. K-Mine offers a mechanism for recalculating mother and daughter seams directly into the database. To do this, first recalculate the new table and correlate the seams before creating the seam block model. You'll need to specify the necessary reference books, the full chronological sequence of seams, and the calculation algorithm. There are two algorithms to choose from. First option interpolates the thickness of daughter seams using adjacent boreholes. For example, if a mother seam 1 is present in one borehole and the seam 1A, 1B, and 1C are found in neighboring boreholes, the thickness of the daughter seam, like 1A, 1B, and 1C, will be virtually interpolated in the first borehole. These interpolated thicknesses will then be considered when creating the seam block model. The second option relies on the percentage relationship between the daughter layers, 1A, 1B, and 1C, and you'll define this relationship in the table assuming the total thickness of the mother layer, seam 1, is 100%. And when creating the new table, the daughter layer's thickness will be recalculated based on the percentage contribution to the mother layer's total thickness. It's important to note that a preliminary analysis of the deposit structure is always essential when modeling. Essentially, deposits can be divided into two main categories: structured and unstructured. Structured deposits are those where primary structural features like layering, mappable changes in lithology, or secondary structures like faults, fractures, and lamination significantly influence the distribution of mineralization. These include sedimentary deposits where mineralization is closely related to primary lithology, such as coal, including low-grade coals like brown or lignite, stratiform-based metals, iron ore, and bauxite. The distinction between structured and unstructured deposits plays a crucial role in geological modeling and resource assessment. For structured deposits, mineralization control is key, and it should serve as the foundation for modeling. Coal quality refers to a variety of characteristics, including ash content, volatiles, moisture, sulfur, specific energy, swelling index, grindability, and more. The continuity of the confining structure, which shapes the deposit, becomes a critical factor in modeling. For example, when a fault intersects with the coal seam, the seam is typically displaced, often resulting in a sharp washout into the rock on the other side of the fault plane. In some cases, coal near faults may become mineralized with the calcite veins or other mineral forming. The sulfur content of coal can also increase or decrease near faults due to past fluid migration, which may have either deposited or removed sulfates from the seam. If faults were active during peat or coal accumulation, known as seam depositional faults, the coal may split or change thickness across faults. If faults were active after the peat and coal had already accumulated, the roof rocks may change in rock type and thickness across the fault. On the other hand, for unstructured deposits, boundaries are often more arbitrary. This might include grade shells based on arbitrary grade cutoff, the observed extent of alteration, or other interpreted boundaries digitized by the geologist to create a solid within which the grade interpolation occurs. In some cases, constraint estimates of grade and other parameters might be used in resource estimation. So when creating a stratigraphy block model, it's essentially to incorporate geophysical data. Borehole logs play a crucial role in seam correlation, offering a detailed profiles of physical properties that display similar patterns of change across boreholes. And this is specifically true when modeling coal deposits. Marker beds, such as tuff layers, side-right bands, can be difficult to identify visually, but they serve as clear markers in geophysical logs. A basic set of logs typically used in a coal exploration is outlined in the table. Geophysical logs are most effective when collected from open, fluid-feed boreholes. However, natural gamma and density logs gathered through steel or PVC casing can still provide valuable data for lithological interpretation and seam correlation. The use of acoustic televiewers and resistivity micromanaging tools is becoming more common for gathering structural and rock mass quality data. These tools can map the frequency orientation and sometimes the character of discontinuities, as well as the direction of lateral stress fields through breakout analysis as shown in the figure on the screen. Many mining software packages now offer features that allow users to plot stick plots directly into on the drill hole traces, aiding in the structural interpretation of bedding and other planar geological features. Bedding and discontinuity orientation data can also be gathered using deep meter instruments. While deep meter logs don't provide the detailed images of the drill hole walls like televiewers or micromanaging sondes do, they are more cost-effective to maintain on site. And deep meter logs still offer detailed, really reliable orientation data, which is crucial for accurately interpreting deposit structure and coal seam continuity. Over the past decades, there have been several key advancements in seam modeling, including the use of seismic data to confirm geological continuity between boreholes, innovations in geophysical logging technologies such as development of borehole imaging tools, and the adoption of geostatistical methods like inverse distance weighting interpolation, nearest neighbor interpolation, modified Shepard interpolation, and various kriging methods such as ordinary, simple, universal, disjunctive, cold kriging, and indicator kriging. Also, enhancement in the surface modeling algorithms that allow for quick evaluation of alternative geological interpretation. That being said, it's important to not overlook traditional resource estimation methods. These approaches can offer a level of rigor in geological practices that newer technologies may lack. Geological mapping and the application of professional judgment and experience in interpreting drilling results remain valuable, even if they are sometimes underutilized. So the data models generated by the software need to be thoroughly reviewed and adjusted if deficiencies are identified. Likewise, geostatistical methods are applied to both structural and quality assessments to ensure that geological trends and patterns are accurately represented in the models that will serve the foundation for future mine design and planning. And K-Mine provides a comprehensive solution to production challenges, offering a full suite of models for seamless asset management. So I think that's it for today. Thank you guys for joining me, and I'll see you next time.